Bom, pessoal, a gente está todo mundo aqui entre amigos, mas mesmo assim, deixa eu fazer uma apresentação que é com muito orgulho que eu apresento o Michael Vorländer, que vai apresentar um pouco do que ele tem feito recentemente. Acho que ele dispensa apresentações para este grupo aqui, mas o Michael é professor na RWTH, escolhi essa camiseta especialmente, onde eu fiz o meu doutorado, sob a orientação do Michael. Ele é professor lá desde 96, dirigindo o Instituto de Acústica Técnica, Engenharia Acústica, onde eles trabalham em diversas áreas da acústica. Mais recentemente foi dividido ainda em duas partes, agora ainda tem a parte de acústica médica. Então ele vai contar um pouco do que está sendo feito lá no Instituto, que é mais voltado na área de realidade virtual, que apesar de ser uma sub-área, ela acaba tendo intersecções com diversas outras áreas da acústica, como o Michel vai mostrar. Eu acredito que a palestra, apesar do Michel falar português super bem, então se vocês quiserem conversar com ele depois em português,
vou falar em inglês.
Mas eu acredito que a palestra vai ser em inglês. Então eu penso que o Michel inicie e eu agradeço mais uma vez por estar aqui no Unicamp.
Vamos fazer a boa. Muito obrigado, Bruno. Eu estou muito contente de ficar com vocês. Primeiro, eu quero agradecer ao Bruno para o comitê para dar uma palestra para vocês. É mais fácil de falar inglês, então eu vou continuar em inglês. At first, I would like to introduce our university and our institute, where Bruno, as he said, graduated with his doctorado. That was in 2013.
December 12th.
Okay, so some time ago. And we are very happy that Bruno is now in the rank of a professor in Unicamp. And this is why I came here yesterday. We had a good conversation with the international office. And maybe the opportunities for next years to come, that in different disciplines, from architecture to mechanical or electrical engineering, we can do some intercambio and all these things together. So this is our institute building. So we are 2 professors, and we have a workshop and the usual staff of research assistants. And we do research in architectural acoustics and virtual reality, in transducers, electroacoustics, measurements, and so on, in binaural technology, and in medical applications of acoustics. This is where Aachen is, so right in the middle of Europe. You have Brussels here, you have Amsterdam, somewhere here, and Frankfurt is here. Best flights from Sao Paulo are going to Frankfurt, so it's a very short distance. Yeah, this is just to begin. Our university has focus on engineering, and we have now 45,000 students in engineering. And my contribution is in the Department of Electrical Engineering and Information Technology, so which is quite the same as this department. And this is why our acoustics is more signal processing acoustics, or let's say electrical acoustics, not so much vibrations like here Ahuda is doing, or what Stella Maris in building is doing. So this is, we do this little bit of this, but the focus is on electrical filtering and all that, and simulation. So this is what I will talk about, signal processing components which are used for virtual acoustic environments. And so just to start with, we can ask, we can ask what is virtual acoustics, what shall we do with that? And the idea is that during design of machines or buildings or urban environments, or like a large square in a city, then all these engineers are very busy with designing all their features, and according to their expertise, they do it basically visually. And they have maybe some databases in the background, but they work visually. And in the with virtual acoustics, we can enhance the design process for such kind of sound engineering with immediate feedback to hearing, not just to the visual feedback. And this is why we are doing this. So we can extend the design by other modalities, and we can include other information also to people who don't know what acoustics is about. But they can hear, they have ears. So we don't need to teach them about acoustics, they can simply hear. And there are many examples such as buildings, vehicles, or even games. So we don't look at sound, but we listen to sound, and then this makes things much easier. And we can also take into account more complex situations where the complex sound field is very hard to explain to laymen, to lay people, but if they listen to it, they understand. And it is a lot of fun as well. So here are some examples. On the top left, we see an inside of a concert hall. On the top right, this is a seminar room for conversation or maybe teleconferencing, which is just a simulated space in this case. Here we have another concert hall, and that's an example of already colors used to highlight some features of acoustics, but it's more interesting to look at this head. This head is equipped with 2 ears, and we can project ourselves into this, what this head is listening in this space. So this is the part of the work which I will explain in a minute. So just for the architects here and the more people working with buildings, this is what they usually do. They use some kind of SketchUp, which is a very famous software environment, to make a space, create a space out of surfaces, and this is how this could look like in this interface of SketchUp. And one of our software is plug-in for SketchUp, so we can simply add more buttons here. We see this button with a play button, so you can go inside and listen to this space. You can see it, but you can also listen to this space. This is one example. So also just to motivate the work, I will start with some demos, which is a completely different example now, which is air traffic, and we can have a look into this. That's an aircraft simulation. We also see the noise footprint here, but the aircraft is flying here, and the person can listen by headphones about this aircraft noise. You see this aircraft has our logo of the university. And that was a map of Frankfurt Airport. So that could be a tool for airport design. So if they are planning a new runway, there will be a lot of political resistance against that. There will be demonstrations, everything against that. But if people can experience what it really means, and that it's not that bad, or we can do this way and that way, this is what is in Europe a very hot topic now. It's called participation of the public. So in all these big projects, the people should participate, and then they consider the project as their own thing, but not if the politics just decide something and people have no chance to discuss. So this is an example of participation. Another example is this one. This is an urban scenario. So we can listen to the birds, and then we can walk in this park. There will be another noise or just sound here, and there's also cars going in the back behind us. Of course, these demos are also useful for headphones, and then you feel it really around the head, so the cars are in the back, and the fountain is on the left side. This could be used as an example for planning of a road near a park. So if people are really happy with the park, but if there's too much traffic, it doesn't make any sense. But if they make some kind of barrier, the traffic goes in a tunnel, and then the park is quiet. This is a big difference. And then we can show how this would be. I think I stopped that because otherwise it's too long. But we can just forward.
You hear the jazz band?
We can also go inside of this Congress building. You see the band playing music. And so on. So I will just What I didn't tell you is that maybe we can observe it here. So stop. This is a so-called cave. Cave means cave automated virtual environment. It's like a small volume, like if you would go into the cave in a mountain, and then you are inside a small box. This cave is a 5-sided projection arrangement where we have the floor and all the walls projected from outside with stereo beamers. This is why the person has these 3D glasses, like you know from cinema movies now, that we can see in 3D. And the person has headphones in order to listen to 3D. So this is all about 3D in this case. So you can go around, walk around, and there's everywhere there's a picture, except for the ceiling. But this is good for us. It's used for ventilation and for getting the people not being unconscious there because of loss of oxygen. But we can put loudspeakers up there. So this is why we can also use headphones, but also loudspeakers to project the sound. This means we have an audio-visual laboratory. So this is also to be mentioned here. Okay, so now I will, this was only motivation and introduction. Now we will start. I will talk about what virtual acoustics is about. It consists of these 3 components. And then I will talk about more or less new attempts on new research, what's going on right now, and what would nice to be in the future, nice to have in the future. So this is the overview. Some of you may have seen that several times. Last time maybe in the ICA in Buenos Aires. I think some of you were there in the Congress. So you remember this picture maybe. It's the chain of the simulation of sound finally ending up at audio files for the headphones. So we need to generate the sound as it exists at the source, which might be this. This is the source. So we have to calculate the impact of my finger on the table. This has nothing to do with the room or even not with the table. It just is the contact point here. Another source is my voice. So it's only what comes out of my mouth, independent of the room or whatever I do. So this is how we can record or simulate the source is the starting point. Then we talk about propagation. We go back to this example. The propagation means that the sound which is radiated from the table is excited from the force at a point, and then the plate goes into vibration. And then this is radiated into air. At first we have vibration of a solid body. So this is the structural wave simulation over then including junctions, maybe the plates are connected. So we have another complexity. Then we have damping. If this is an aluminium table or a wooden table, it will sound quite different. And so this is all in this part, although the knocking of my finger is still the same. But the sound is very different according to aluminium or wood. And then it might be radiated into a space of air, filled with air, which is usually a room, or it's an outdoor situation. And finally, there's a listener. So some person with 2 ears, with a head, and so this is related to the sound reproduction, which creates then the sound which can be played by loudspeakers or headphones for the listener. So this is the separation into the 3 components. In some parts here between the generation and the propagation, there's also feedback. And this happens when the properties of the source, for example, with my finger and the table, they have some interaction. And this people in electrical engineering are very familiar with that. If they have a voltage source and they attach it to a network, then the current which goes into the network depends on the voltage, on the inner impedance of the voltage source and the impedance of the network. And you connect 2 impedances, and this is not at all trivial. It's only trivial if one impedance is very much larger than the other. But usually they are in the same order of magnitude. So this means we have this interface. For my voice or for a violin or trumpet played in a room, there is no such interface. So it's easier. Then we just have a forward direction. Because if I play a trumpet or if I'm talking here, my voice generation is independent of that room. I would talk in the same way outside. there is no feedback to my vocal folds by the sound field. But in this case, it is. So we have to be clear. Also for the compressor noise, which is now here in the air condition, this makes a vibration. Then we have 4 screws on the wall. And so we have 4 contact points of force, which excites the wall. Then it depends on what kind of wall is that. Is that a heavy wall, concrete, is it bricks? And how are they all in phase, or do they something like this, or do they even rotate? Then we go into, for the structural acoustics experts, we go into many, many more complexities, and it may be 6 degrees of freedom for each point times 4. So 24 input data are used at that point with an interface. So it might get very, very complicated to simulate what we are listening now, a compressor in a building. But in principle, it's all the same. It's all covered by this slide. It's just how much effort we need there. Okay, this is the physics part. Now we draw that down into a signal processing model, which does exactly the same. The source is nothing but a wave file, an audio file in the end. It might represent my voice, or the compressor sound, or my finger nodding, but it's just the original sound. Then it goes into something which is characterizing the propagation path. And this is an impulse response. And we know from signal processing very basically in linear and time invariant problems, this just needs to be convolved, and then we can see how the source runs through the filter, and then we can listen to that. So it's a very simple approach. In the end, we have a discrete convolution of this system, which illustrates exactly this little box here is exactly the same as was here. So the green, the yellow, and the red are doing the same. Okay, so as I said, this should be linear. Mostly acoustics is linear, unless we have extremely high levels. So okay, that's not a problem. This should be time invariant. That will be a problem, because of course this is now stationary. But if this is time. So, perfect timing. We have to discuss how to deal with that, and maybe you remember in the video, the person with the aircraft simulation also walked around, and he did something, because this is not a static situation, so there's something changing. We have to deal with that as well. So here there is already from the 1980s, there's a lot of theory and numerical methods available to calculate the propagation, which is then how does the sound get from the source to the receiver. So that can be done by ray tracing in this case. That can be done in building acoustics with some models for characterizing the construction elements of a building one by one, and then you put it together. You can calculate the sound transmission through flanking elements and so on. Also for outdoor sound propagation, there's an atmospheric model for the aircraft, for example, or from a train track 5 kilometers away, and the question is how does the sound get 5 kilometers to here? This is all including wind and temperature and humidity data and so on. So this is all very simple. We can use that. On the other hand, there are rather exact solutions of the wave equation, which are very hard to calculate, but we can go back to the wave equation and solve that. Basically with numerical methods of that kind. So for boundary element methods, or finite element methods, or finite difference time domain methods, this is very rapidly going on. But there's not, nothing especially new. This is ongoing progress. And the same for geometrical acoustics. This is the little video you see here. This is only geometrical acoustics, and you can use image source models, ray tracing, and mixes of that to take it. So in the yellow box is all very well-known theory and methods available. So this is what people do with this ray tracing. It can be different, you could say, dialects in software which are available just to be used. Usually in rooms such as this one, this is applicable for the early part, which means the sound which arrives quite early after maybe having suffered one reflection or two reflections. According to the speed of sound, 340 meters per second, this lasts some milliseconds, maybe 10, 20, 30 milliseconds, which is also quite relevant for our hearing. We have learned in psychoacoustics this component is very important to be precise because our hearing is sensitive to that. The hearing impression is very much depending on what happens there in the so-called early response. And we can calculate that quite precisely with this cone or beam tracing. And later we can also do this one, the classical ray tracing, which is just a stochastic method for the later response. In acoustics we call this reverberation, which is later than some milliseconds. So it can last 1, 2, 3 seconds later. But here our hearing is not that sensitive. It can be just a mix of stochastic things, so which is still okay. And in the end, in a simulation, it would be like this. This is already a filter which can be used for this kind of convolution processing. The red part is the exact part, image sources and specular reflections. So from the ceiling, the sound bounces back from the ceiling and comes to you. It may be this one, and then there might be one to the back wall, ceiling, and then coming to you. And and this ray tracing things are the blue one, which is kind of scattering at the edges, at the tables, and everything which is more stochastic, which is this energy is calculated in the blue part. And if we put that together, we have a good model for the sound field physics for that problem. Can be also applied for outdoor problems. For outdoor situations, it might be only the red component, because we have a direct part, then we have a building which reflects the sound, and another one, and some buildings, but there is no late reverberation because there is no closed space. So this is not just focusing on rooms, but also for outdoor spaces. We can also simulate rooms which are coupled in a building. So in this case, we have one floor with several rooms, and they are connected with doors. So all these simulation models can calculate the response inside of one volume and also in the other volumes, and they are connected by walls and doors, and this creates now not just a filter, which was here, one filter, but here we have several filters, one after the other, from one room to the next room to the next room to the corridor. So we can also calculate the sound through several building elements. Of course, if someone is talking on the phone here, it is very rare that someone in this corridor can notice that. So it will be very high intensity required for that. But for one room to the next, or maybe one room to the next, and also through this corridor, if the two doors are open, then we can also use this part. So it just depends on what people are doing in that. If the doors are all open, it's all connected. So this kind of processing will lead to a filter chain, but still the same. We have a sound source here. We have all these filtering characterizing the volumes and the structures. And in the end, we end up with two resulting sounds for the right ear and the left ear. We can put that to headphones. I can also demonstrate that. This is an example of the so-called Unity framework, which is a famous software environment for virtual reality, for gaming. So this is made in Unity. We see this kind of shopping center, and then we have a road, and here's a building. We will now go inside of this building. We will focus on that one here. And we have a room here, and another room here. And this is what is now simulated. And I'm simulating now a room, I should say that again. So the source is here. There's a TV set, and here's a sofa. Someone is watching TV, a TV show or sports, a football match. And another person is here, but that's a bedroom. So there should be quiet. And let's listen to this, how this will be if in the next room there is just music. So like this. It can be like that. At home you would listen to music like this loudness. And then in the neighbor's room it sounds like this. So there's still something. So it can be upstairs or it can be next door. Now you should imagine that you like to have in quiet, you want to read a book or you want to sleep, and then you have all this, right? Or they let's put that, a TV show, maybe a little more level. not very loud, but it may be very annoying in such cases. And so this can be used for demonstration for, okay, if we make the wall a little bigger, it may be like that, and so on, right, to decide for another construction. But it's also useful for research, and this is shown in this video. So here we have the scene again. It was made in Unity. We will now fly into the building, and then I will explain later what we are aiming to do with that project. So that's, there will also be sound coming later, but not yet. So now we are going into this example. It may be an office building, and here we listen to the sound. Maybe that's even too loud. So there's some kind of sports event on the TV, but this is not in that room. This is now the wall transfer. You see to the neighbor's room. So this is where the noise comes from. And we will use this demo to stop here and let the people sit down at that table and use the laptop in this cave. I mean, or with an head-mounted display, so people can sit down. And then they have to do something, but it's not about acoustics. They have to learn to read, to calculate some problems, and then we measure how good they are in this. And we do this with and without noise, or with changes in the noise. So this is a so-called cognitive performance test. One example is memorizing telephone numbers. So there will be read some one-digit numbers, 1, 2, 3, 4, 5, 6, 7, without 7 because it has 2 syllables. 1, 2, 3, 4, 5, 6, 8, 9, 10. And then you tell the numbers, and then people have to repeat after a minute, and they make errors, and we just count the errors. And they will make more errors when there is this TV going on all the time, because they are distracted from the problem. So this is how we can measure the annoyance or the impact of noise without questionnaires. I'm not against questionnaires, but I don't like them. Because the questionnaire is always an artificial laboratory situation. You can invite a population to come to the lab, and then they, okay, are you annoyed by this? Then we ask them, are you now annoyed? For example, here. No, are you annoyed? And people say yes, but how much? I don't know, maybe 7. So this is not very straightforward. But if we don't talk about acoustics at all, and we just ask them, please do this telephone number problem, and then this is just switch on and off, they don't know what is the sound about. And that's a better way in getting information about the real need for the sound insulation in case of offices or classrooms, or maybe at home also for leisure. But this method would be to measure the performance in working and learning environments, because this makes a difference if people can memorize well or not. And the work output and the performance of the people depends on the acoustics. That's clear. So this is what is the project about. So the computational cost for the demo which I just showed is not that bad. For the sound insulation matrix, we just need 30 milliseconds to calculate that on this kind of computer, on i7. The filter construction is very quick. Then if people walk around and they turn their head, we need to update binaural and headphone data, which is just 7 milliseconds. And then for the convolution, we just need 0.1 milliseconds. So this can be done even if the computer is running all the computation. And the people in this performance test, they can also move and they can turn the head, and the computer just adapts to that. So this makes the test even more natural. They should behave as naturally as possible in this kind of test. Okay, now I will give some perspectives for what is the progress for next year's work. Of course, we will have more precise simulation models, but as I said in the beginning, it's not completely new approaches. There's no new physics. The physics is there. We simply need better models, including wave effects, to characterize the sound propagation from the source to the receiver. A little more precise. But we also need better 3D audio. And that's the bottleneck at the moment. So 3D audio, there are very excellent PhD studies on 3D audio by this guy here in the front, for example, but there's still a lot of movement because also the gaming industry and the audio industry is jumping on that because of games and of big business in that. And this requires tracking and real-time processing and all these things which are coupled to headphones and head-mounted displays. They are very cheap at the time being. They will get much cheaper in future, and the big ones, including Microsoft, Google, and Apple, they are on that now. Facebook. And Oculus, even Facebook. They are very much in this, and they spend billions of dollars. So a little university has no chance usually in this. But they just founded departments of research and development with many PhDs from excellent universities, and they do it on their own. They don't need us anymore. So, but this will come. In programming, of course, we can, but this is more related to the simulations. If we can do more efficient programming, we can make bigger scenes, not just the room to room, but maybe more complex, including an aircraft flyover and the traffic is running on the road and everything comes together. But this cannot be done on a laptop anymore. And so more efficient integration and programming will create more complex scenarios which are even more like real life. And of course we need to check if everything what we do here is exact. So we need better and more sufficient human interface feedback and evaluations of that. And just in order to check if this what we simulate is authentic or at least plausible. Or if this doesn't look very much real, but it's for a computer game it's okay. But if you like to see what is this details in this grass, this is just a green flat surface, and so it could be more real also in the graphics. So computer graphics will be used for that as well, but for the sound it's the same. This is not as real as it should be, and the same is true for the immersion and realism just for the modality of sound. Okay, this perspective is interdisciplinary very much, so we need all the developments in three domains. In acoustics, we can deal with better models and better material data, which is our task. This is what we should do, better material information. How can we use the carpet and all that and this kind of thing. And better models. In signal processing, there are very nice approaches for variable delay lines, temporal and spatial, spherical harmonics processing, and also for time variant systems, because I would like to move around in my scenario, thus in normal behavior. I should not be forced to just sit in a static position. So that's a lot of new challenges for signal processing. In psychophysics, which connects our perception with brain models, it will be interesting to see progress in HRTF, binaural hearing, but as I said, it's Google and Facebook are on that already. But also computational acoustic scene analysis, CASA multimodal evaluation is where the visual input and the auditory input will be processed together in order to judge if this is a plausible or authentic situation in which we are. And we should be as authentic as possible, of course. So I will now, this time is okay. I will now go into a little more details on signal processing. That's in the title anyway. So, and then we will finish, if there's time left, with some psychophysical ideas. So for signal processing, it's that part. The first I can notice is that the convolution is more or less, also with a low latency, is more or less solved, I could say. Even on small computers, it's no problem anymore to convolve just an incoming audio stream with the filter impulse response of the propagation path. So that can be outdoors, indoors, anything. The impulse response can typically be of 2 seconds length. 2 seconds length means 44 kilohertz sampling rate, let's say 100,000 samples or filter coefficients. This is the size of that at times 2 because we have 2 ears. And this is just now, since 2 or 3 years, possible on just a laptop computer. That's no problem. 20 years ago, you needed a huge machine, so-called Convolvotron, from Lake Instruments from Australia at that time. They were the first to do that, and it was a big machine, but today it's the laptop. Maybe even the smartphone.
And the cell phone.
Yeah, maybe a smartphone can do that. So a very important word on this slide is low input latency. What does this mean? We don't know the audio stream. It can be just a recording of something which happens right now. For example, my voice. So we don't use it from a CD or from a data file. We just can use any audio stream. But the processing should deliver the output immediately. Because when I use my own voice in this system, I should get my feedback to what happens in this room now and not after 1 second. This would create terrible echo with a delay, which is not physical. So this means latency, if there would be a delay. So a low latency means it's an inaudible delay, only with a certain limit that my ear is not sensitive to that delay. This means the processing shall not exceed a certain time limit. And the way to go there is like this. The problem as well is this is time variant because I can walk around in my virtual world, which means that the processing must be repeated for every position. The question might be, how often do I need to repeat? Just for 1 centimeter or just 10 centimeters? So, but that's all, this is known. Anyway, the way to do that is using filter techniques of so-called partitioned FFT convolution. This is now a little more signal processing details. You know who made that? You see the name here.
Yeah, I know.
So you know this work. And that's about, I just focus or highlight the numbers. If we would do that just straightforwardly, we have 2 seconds of binaural impulse response, which means 2 times 88,000 filter coefficients must be multiplied and added. This can be done straightforward with an FIR tapped delay line. So this is just a straightforward FIR filter. And this has no latency, which is very good. We don't like latency. But this needs 200,000 floating point operations for each sample. So the samples come in with 44 kilohertz, and for each sample you need 200,000 40 point operations. This is with a big machine, it's no problem, but it's a lot of processing for just 1 sample. And then they come 44,000 per second. So if we do that in another way, I skip all that details, but we can, if you like, you can ask, we can come down from 200,000 to just 400, which is a saving factor of 240, with basically exactly the same result, mathematically exactly the same result, but we have to pay this with 6 milliseconds latency. Now the question is if this is okay, 6 milliseconds, and the psychoacousticians say 6 milliseconds is relaxed, that's okay, you can do that. So if we do this, we can save a factor of 240 of processing time, which means, on the other hand, we can process 240 times as many sources as in the first case, in parallel with the same computer. And this means instead of using just 1 car making sound, passing by, creating the noise, we can process 200 cars. A real highway, a big highway crossing with the same computer. This is a very efficient way. So this is done by converting the time domain impulse response into spectrum data with the FFT. Then instead you know that the convolution in time is a very complex process, multiplication and addition. In spectrum it's just a multiplication. And then we need to convert back to the time domain by inverse FFT. This takes some overhead processing, but still this saves a lot of processing time in the end. And if we do that with the partition means we do that in blocks. These are the partitions. Also the impulse response is in a block.
And if we subdivide the blocks in an efficient way, we can get this. Okay, now some more details about signal processing, or new challenges and new benefits from modern signal processing. This is about around 2015. It became more and more famous, used by many people in our lab as well. It was, when did Martin graduate? Also 15? And Bruno and Martin Polo were the first in ITA who did that. Now it's continuing with other people doing research on spherical harmonic mathematics and multiple input, multiple output approaches. So this connects the source and the receiver and the listener. And it opens very many new applications and technological implementations. So I will now talk about the source and the receiver. And we have to do this in a spatial way. And one picture showing this is a little room for maybe concerts. That's a simple model for the Concertgebouw Amsterdam, a very famous concert hall. And here should be a sound source, and this should be a listener. And what we see there is not really the sound source and the listener, but a mathematical representation of them, and only part of them. The so-called spherical harmonics, they are just a matrix, or we could say a list of spherical shaped functions. The lowest shaped function is a sphere. The next complex shaped function is a dipole. There's one example for a dipole. Then we have a quadrupole, hexapole, and so on. This is a hexapole, so it has 6 lobes. And the theory says it's very much similar to the Fourier transform, that if we take them as base functions, in Fourier transform it's sine and cosine functions, and then we add them to get any sound, right, any overtones and so on. But this is the same concept, but in space. So if we have a spatial function, which is usually like in antenna engineering, a directional function, the antenna gain, are there antenna people here? No, so
I don't think so.
But you have antenna people in the department.
Yes.
Yeah, so they would do the same basically. So they would describe the spatial shape of the beam for the antenna by some mathematical shape. And if you decompose that into spherical harmonics, you simply take the base functions, which is sphere, dipole, quadrupole, hexapole, and so on, and add them with some coefficients, with some weighting, which is the spherical harmonic spectrum then. This is the weighting factors. Now, if we do all the simulation and calculation and or even measurements on this basis, we can connect the dipole to the hexapole. But we can also connect the monopole to the monopole, which is classical room acoustics. Dodecahedron and point microphone. This is monopole to monopole. But here we see more. We see dipole to hexapole. We can do monopole to hexapole, monopole to dipole, dipole to monopole, and so on. We can connect all of them, which spans a matrix, or you could even call it a tensor, and it would connect the spherical harmonic here with the spherical harmonic here, and we connect all the impulse responses with these weightings for all these sound paths in one impulse response tensor, and we call it shirt.
Tensor because of frequency?
Huh?
Tensor because of frequency, right?
Yes. And all this complexity, so it's a three-dimensional thing in the end. Yeah, this was created, or one contribution was by Haim Morgenstern. He was from Ben Gurion University in Israel. He is now in Unicamp in Paris. Okay, so this is how it would look like. This is the big tensor, n times m, dipole to monopole and so on. And now if we map any kind of receiver on that and any kind of source, we can even let them rotate. So for example, a musician with a violin could maybe play it with a very high expression of music with some movement, and also the listener can do this and to listen to the sound. And these operations can be added later, and they are very, very cheap as concerns processing. So this is variable. Also, this is very easy to include that, and this is created only once, and later this is again very cheap, and this can be also added later. So if we, just in short again, if we do this, we can later let the source be a trumpet or a violin or a bass or a tuba or trombone, and the listener can be me or you or you or you or you, or it can be a system, a surround sound system for everybody. This can be added later. So again, in room acoustics of today we have point to point. But if we do like this, we can do later anything like a specialized or special source, radiation characteristics, and we are more flexible with the listener as well. Okay, this would look like, then we need directional data for these instruments, and that's another component. So we are not the only ones in the world who are doing this. So this is one sphere, I think, in Aachen University, Salt Lake City. This is in our lab.
That's in Graz.
Oh, that's in Graz? Yeah, could be in Vienna. This is in Finland. This is in TU Berlin in Germany. And here we see some spherical things with microphones. So while the musician is playing, there's a simultaneous recording of the microphones, and later it can be processed into this antenna gain, what we call in acoustics source directivity. And what we did, and it was published some 2 years ago, also for open access, all these instruments are now measured, and all these single tones in chromatic scale, so you can do pianissimo and fortissimo, and so all the tones create different beams in this radiation pattern, and now you can just use that from the internet for any kind of application. So this is available. Let's talk about that. For the reproduction of our virtual acoustics, we have also a directional component, which is ourselves, because our hearing has a head and pinna, and also for this, there is you can use a dummy head and characterize these directional functions for the dummy head, for binaural processing, let's say for loudspeakers or for headphones. But if we don't like to use this because we are not sure if it is the best solution, we can also use my head for that. At least if I would do that for me, I would prefer to have my head here, not this one. So how to do that? Yeah, we can put them in this arc. This is the second arc we made. Did you see that yet?
Yes, I did.
Yeah, so that's because the other one had a problem, and then we made a new one, which is just many loudspeakers are here, and they are they play sounds one by one, and then the two microphones in the dummy head's ear, or in my case, I have little microphones in my ear. We can calculate all the different directions for the hearing, and then this rotates one revolution, and it takes about 5 minutes. So you have to sit there, and in 5 minutes we have all these information. It's also a directional function, like for the source. It's all reciprocal anyway. And this is a very nice project on that part, a progress on that part. And we can also discuss, I think this is also in parts. Also so-called ambisonics systems, where you have several loudspeakers, maybe 30 loudspeakers, creating that sound. And the basis for this kind of ambisonics coding is the same mathematical basis anyway for the spherical harmonic. So it's a good match. So we can choose to do this or that in a flexible way. We can choose here and we can choose there with the same simulation. Okay. So the design for that kind of processing, however, is very challenging, and we must face the truth at the moment that frequency range where this runs well, we're matching one spherical harmonic arrangement with the other one, with basically on spherical microphone and loudspeaker arrays. If this is processed in a joint design between the receiver and the here we have the spherical harmonic expanding for the receiver and here for the source, and that's just the sound propagation in Green's function between them. If you solve that and optimize in a joint way, it can only serve for one octave. That's not enough. So It depends on the size of these spheres, and there are many, many factors in this design. But the idea is fine for this shirt, but it doesn't work for the whole audio range, just for one of them. So people do it anyway, they just forget about the errors and they just do it, but it's not very precise. Okay, so this was my introductory slide again, interdisciplinary problems. Here was the sound field physics, and we just talked about that part. Now a little bit more about psychophysics, what's going on there and what can be done there. So I can report about this project, which was finished last year, the so-called season project, with many, many people involved, many universities involved. Telekom Labs in TU Berlin, Oldenburg University, Ben Gurion University of the Negev in Israel, TU Ilmenau and Fraunhofer Ilmenau, and ourselves, and with these names. And we were focusing on the quality of such kind of audio simulations, basically for perception of music in rooms and speech. And this involves a lot of virtual acoustics as well. And here we see an extended version of what I was talking about, of a source to receiver model with the propagation in between. But here we couple the audio with the video. So the starting point for the sound is the violin recording in an anechoic chamber in a special acoustic laboratory. The equivalent for the video is a green box recording of this string quartet in a green box studio with video cameras of binocular camera in order to see depth as well. For the singer or the speech is the same. That's a speech voice in the anechoic chamber, and here it's a drama expression of some theater speech in a green box recording. So this is the source. Then this is put in a 3D environment. This is the Gewandhaus in Leipzig, one very nice concert hall. So you can put the string quartet here. You see in the video that they are playing, they are moving. It's really very realistic. Also, this is a picture which is taken from videos and photographs. It's not a SketchUp model. It looks much more realistic for this reason. But just with a mouse click, you can put them in a church, and you can switch that. Right? So it's the same. They are continuing playing. They move. They do everything what they did in the video, and then we can play around with that. And of course, this is not just for the presentation here. Later, people will be in a situation like that. So here's our test person on a chair. This is a hemicircular or hemicylindrical projection screen. So the person has also glasses. You see basically all this space in front. People can move and so on. Of course, it's played with a proper headphone, which is a very complex headphone arrangement in order to have the audio correctly. And then we can play the sound of this room, and we can show the video of that room. Or we can play the sound of that room and show the video of that room, or we can show the video of the same room and the audio is in the same room. And we can play the sound without any room, or the sound with the outdoor. So you can mix everything. So this is now about audio-visual interaction. And the question is, if we see something, do we believe more that what we see or what we hear? And what if there's a conflict? And that's about psychophysics perception, very important for virtual reality, because both should coincide as best as possible. But maybe in some examples we can relax and just forget about precision. If the video is perfect, maybe the sound is not necessarily to be perfect, but we don't know yet. So
how are you going to ask the subjects if they're...
Yeah, but in Berlin, this is Hanjo Mempel, who is in the group, or was in the group of Stefan Weinzel before, but now he has a job in this museum of Philharmonie, in this Musikinstrument Museum. But they made a lot of cross-modal interaction effects, and this is based on exactly a questionnaire, but with many items and factors which are characterizing the sound quality in terms of brilliance, coloration, reverberance, loudness, and also this will be asked, and then they do this repeatedly with different videos and different audios and see if there is any statistical significance between them.
Yes.
Yeah, so that's all this. Also here we have 5 projectors in having a high resolution. These are the projectors, a high resolution video on that screen. Did you see that once? It's in the main building in Berlin in the upper floor. Okay, so and another example which we were working about until last year, it's about immersion. Because immersion is a very hot word now in gaming. And if people do this driving or shooting games or whatever, or even football games, this FIFA football game, it's all surround sound everywhere. And the aim is to put the player inside of the computer, just by thinking, to be immersed by this virtual world. And yeah, so there are some statements by other people. What is the immersive, what is the best immersive audio in entertainment industry? And they say it's not just the horizontal plane, we must play sounds from everywhere, otherwise it's not immersive. So sound from above and the back is very important. And this is why, this example, one of our PhD students, Michael Kohnen, he has this HMD, so this display on his eyes. And this is a surrounding loudspeaker array. And then the question is he now highly immersed or fully immersed? How much immersion is there, and what is there any quantitative metric for that? Of course it's not. Although there are some products on the market which say, our product is 10 times more immersive than another one. So how can they know? Because this needs a metric where you can scale it, factor of 10, but this is not existing at all. So what we did is we asked Angela Kulzmann from University of Kiel in Germany. She is from psychology department. We cannot do this on our own. We need psychologists. So and she made a diploma thesis in our lab together with Lukas Asberg and Michael Kohn and myself. So she was in the VR group, in the virtual reality group. And at first she studied in literature what is known about immersion. How do people feel immersed in where they are, and how can we put them out of where they are and put them to somewhere place else, like you would try to do in a cinema. Then the people should not think about that they are sitting in a cinema, they should consider themselves to be in the movie, because they are so much immersed and attracted by the situation that they feel to be somewhere else. So, and this consists of 4 different independent groups. One is causality. Causality means just what happens in the virtual world should have some meaning, some physical meaning. So causality, if there's a cause and an effect, it should have some real physical meaning. Then the room should be perceived correctly, that the space perception is exact. Feeling like in a small cabin or in a big space, this should be rather precise. Then the connection to the source should be there. You should identify really where is the source, if you see it and hear it. And the last point is, which you don't know, you don't think about that immediately, but it's attention. That the attention of the people is drawn to the virtual scene and not to something which is going on in the lab. So if you're sitting on a bad chair and if it's too cold, then the attention goes to the cold laboratory, but not to the virtual world. So these are the 4 points, and then Angela developed a questionnaire with different items where she dealt with all these 4 things. So 9 items, 17 items, all in German questions. One example here. How intense is the impression that your attention was drawn to the acoustic scene? And then people can rank on a scale between 1 and 10 how much they feel that they are in this attention thing, which is the last one. And the other one was dealing with naturalness, reference and inclusion of causality, source and room and so on. Yeah, and then with this test questionnaire, we can test the hypothesis number 1. A high immersive scenario will be rated with a higher number than a low immersive scenario. What is a high immersive scenario? it will be a scene where we are in a room and many things are going on around us. And in contrast, a low immersive scene is only that we are in a free field outside and there's only one source in front of us. Right, so this is a different perception. And then hypothesis number 2, the spatial audio system, which is used for the final reproduction of sound, that will be much higher for spatial audio of high quality than for just mono. Mono is just a loudspeaker in front. Right, but it can play the same sound, but it's just a different loudspeaker. This was the 2 hypotheses, and then we expect that the high immersive scenario is above the low immersive scenario, and this should even increase if we go from mono to stereo, like at home for simple stereo, and then we go to anything else, which is surround sound technology. Vector-based amplitude panning, crosstalk cancellation, higher order emisonics, wave field synthesis, all this. So this should be the best one we could use is this one. So then let's look at the data. There was some, no, I don't have the data here. Sorry, but it was confirmed. So in this thesis. Okay, time is running. So that's already the summary and the outlook. I talked about virtual acoustics in these 3 components of simulation, signal processing, and 3D audio, and what can be done next. New research. The outlook is just what I'm talking about now. We are facing still obstacles. So our outlook, let's look through these devices. This is the famous Oculus device, which is now, I think, $200 or $300. So it's not a big amount of money. It's not nothing, but people can buy that. So, and they buy it for computer games, but we will buy it for reasonable applications. And you see that there are headphones used for that. We will use that for this annoyance test, for the performance test in the buildings. This is our next listening test. And so that's for the outlook through these devices. But still we are facing problems with uncertain input data for our simulation, materials, building materials, and so on. The user interfaces are much too complex that people cannot simply push a button and then the simulation does the right thing. It's not like that. The consumer hardware, however, is there, but it needs to be calibrated very well to have a precise performance according to the physical input. For a game, this doesn't matter at all. I just can put another volume and I can play 2 different colors and whatever I do for the game, that's fine. But we like to have a precise level, coloration, everything should be as exact as possible, representing the real world. And this needs to be calibrated somehow. So that's our obstacles, so we have to fight to get rid of them in the future. Basically that's it. Finally, some outlook for other applications. Of course, this is where virtual acoustics came from, for performing spaces for music and speech to enhance the design. But now we also go for classrooms and offices and for sound insulation, as I told you, that we extend our applications to that. Coming from music more to noise and to noise. For outdoor environments also, I talked about the aircraft noise project. We will have a running project and another one on some kind of helicopters for individual flights as an air taxi. So what's going on now in the world is that we will have air taxis. I think in Emirates, in Dubai, they already have that. That you have an unmanned drone where you can fly as with 1 or 2 people, and then the drone brings you to another place in the city without pilot. This will come. And we will have another project on that next year. So where the idea is to bring you from the city to Viracopos just in 10 minutes without traffic jam on the road. Of course, you will not have a long distance flight with this kind of thing, but from here to the airport, okay. Or maybe to Congonhas, and then you have, why not? But there's a lot of drones already and helicopters in São Paulo, so it's not that easy to add more. I don't know. But in Aachen, there's nothing about that. And in fact, they try to do that on Merzbrück, on this little airport in Aachen. To have this service to take people in Aachen and bring them to Maastricht Airport or to Düsseldorf. Anyway, so this is outdoor, but it will be a lot of noise, additional noise from these helicopter things. And people will not like it, because it's another noise source. We have to take care of how this will be. And so it will be another design tool and component, such kind of soundscapes, where you have all the complete environment together, of natural sound, traffic noise, and so on. And I already talked about this participation, which can even be done in online games. We did this together with our colleagues in Naples, in Italy. So they made a copy in a computer game of a square in Napoli, and where people could sit in a cafe, and then the traffic was going, and then they did some tests with the people in order to check if this or that solution for the planning for Napoli City Council is preferred by the people. And this is called participation of the people. They could go there and do this test, and then the majority decides, not just the city council decides. Yeah, these are some outlook projects. We need more synergies with audio engineering. To my impression, there is a gap between the community of audio engineering, also in the Audio Engineering Society. They do only their consumer electronics, TV, audio thing, and we do our physics on the other side in acoustics, but we need more cooperation with them, because they know very much about all these loudspeaker systems. Yeah, of course we can use everything which I was talking about also in education and training, also in training of architects, for example. There's one PhD project just finished now with a visiting PhD student from Barcelona University, and he will stay as a postdoc now, but he had a very nice idea. He was in an architecture student class, and he gave them headphones, and he didn't show anything, he just played a scenario of a building. So someone was going up the staircase and then was entering a big room. Why a big room? Because it was reverberant, and then he was going into a corridor, and so this was like a movie, but only audio. And then the architecture students had to draw a building. Just by imagining the sound they heard, and what is this building? This is a quite different approach, and this is a very nice idea. So let's see what we can do with that. This is for education, that they will be aware of the sound in that building, and not just by the visual. Okay, so this brings me to the end. It's only 11:10, but I have to thank all these people, which are past PhD students, but also actual PhD students like Lukas, Imran, Jonas. They are still there, but the others already finished. And I have to thank our virtual reality group in our university, which is in computer science, and the colleagues from this season project, of course. They contributed a lot. Okay, that's it. Muito obrigado.
Thank you very much. I expect there are some questions. Se quiserem perguntar em português também.
Você comentou sobre a possibilidade de estudar espaços, né? Você falou sobre a questão das escolas, e a gente tem aqui problemas às vezes de espaços como a gente chama de office plan. É uma possibilidade também de usar esse sistema para...
Não, mas precisamos mais melhores modelos para difração. Difração é um problema na simulação, mas no princípio é possível.
I have a provocative question. You said in the beginning that we should avoid questionnaires and look at different ways to measure perception. And then in the end, you're talking about how to evaluate VR or AVR, and then you show that the psychologist to develop the questionnaire.
Yes.
How to go? It's good to have the questionnaire at this point, but then we have to think on another way to evaluate surround systems that are not based on questionnaires. Did you have any ideas on that? What could be done instead of questionnaires?
Yeah, but I cannot imagine a performance test which is used for ranking of the quality of audio systems. I think we still need questionnaires. I was just talking about, maybe my statement was too general. If we talk about annoyance and noise impact, then I don't like questionnaires, because in the questionnaire it only remains loudness as a factor of significance. Because people would like the sound which is not that loud than another one. But no other parameter is really meaningful. This is why it's more clever to let the people do what they do in this work or living environment, and use the sound only as a moderating thing in a quite a different test, which is the performance test. This is related only to noise and annoyance of noise and impact of noise. But if we go for a sound quality thing about a spatial audio or MP3 quality or whatever coding, what is a better codec, then I'm afraid we still need a list of factors which have significant impact on this sound as such, and there we still need questionnaires. But it doesn't make sense to use a performance test and play sound from binaural or ambisonics. I cannot imagine how that test would be. Of course, you can make errors as well, like in calculations, and you can measure how many errors people do if you compare binaural to HOA. But what does it say then? You don't know what's the. So I'm not sure.
Know what. So one idea that I plan to do here is, together with the with the phonoaudiology department, is to measure brain activity during different reproductions, using different reproduction systems.
Yes.
I have no idea if that's going to show any difference, any significant difference, but that's something we want to experiment first.
Yeah, but that's a big idea. Because the brain region is quite advanced, and they try to track where is the space coded and where is the pitch coded and where in which nucleus is this and that. So what you will see is that the brain has some lights here and there, but if you can see differences between the stimuli, if that is precise enough, I don't know.
That's
the data are quite noisy usually.
Yeah, that's exactly what how we will start evaluating this, to see if we can measure any significant difference.
Yeah. But you are connected with Piotr, right?
Yes.
So he's in that kind of thing with the 2 years and this other project, and they talk about this kind of things. If you have elevation cues and they are not precise, what does it mean for the EEG? So maybe you can write or see what Piotr produced in the last month. And this is an open group, I think, with ABBA. You can simply work with them. And the AMD is open anyway. This is this produces this brain patterns. The auditory modeling toolbox. You have a binaural input, and then this gives you some visual map or some graphics of what the brain does.
Yeah.
As a model. So of course this is not true, but it's a step forward. And one idea could be to feed the binaural sounds either from HOA or from headphones into that, and to check if there are differences. But as far as I know, there is the standard deviation is still much bigger than any effect you can see. Okay. Anyway, I prepared the slides in PDF and I sent it to Bruno, that people can also use the slides for later.
Ok. Só eu agradeço todo mundo por ter presente. Agradeço ao Michael por ter vindo e dado essa palestra, mostrar pra gente para onde a gente pode ir, o que a gente pode fazer. Muito obrigado, Michel, por ter vindo.
De nada.